Good afternoon, everyone, and thanks for attending the CSP seminar. So today we are really pleased to host Yanjun Han. So he's an assistant professor in the Department of Mathematics and Data Science at NYU. Prior to this, he was a postdoc at MIT and UC Berkeley, and he did his PhD in electrical engineering from Stanford University. His research interests are broadly in non-parametric statistics and information theory, and today he will tell us about approximate independence of permutation mixtures. So please join me in welcoming our speaker.
Yeah, thank you, Shubhanshu, for the nice introduction and also the invitation to the seminar. So I'm pretty excited to give a talk here, especially when there is a Shannon schedule here in front of the department. So so today I will be talking about some technical talk probably. I used to give accessible talks, but this one might be a little bit technical. Yeah, because the main challenges we solve in this work are pretty technical. So you might get confused, but I mean, just feel free to ask me questions. Yeah, so before you get too confused, you with anything. Okay, so this is a joint work with my great colleague, John Nelsweet. We are also at NYU. So, so here is a problem setup. Suppose we have n probability distributions over the same space. So what do we mean by a permutation mixture? So a permutation mixture, so basically, just consists of an independent random variables z1 to zn. So zi follows distribution pi and they are independent. And those variables are hidden. And we will also draw a hidden uniformly random permutation pi, which is uniform over the symmetric group of size n. And now we can define our permutation mixture to be the distribution of x1 to xn, where xi is z of pi I. So we permute the coordinates of the random vector z according to this random permutation. And we form the final vector x, which is n dimension, and Pn is a joint distribution. So this is an n-dimensional distribution. Or in mathematical terms, we can also write the permutation mixture in the form like this. So this is indeed a mixture of some product distributions. Okay, so the main target is to understand this permutation mixture. And the simplest idea is to just use an i.i.d approximation or mean field approximation, thinking that, if somehow it's a folklore that probably permutation or random permutations only induce very weak dependence across the coordinates, then how about we say that, in order to understand a probably very complicated permutation mixture Pn, we just assume that the coordinates are i.i.d. So what is the marginal distribution of each xi? This is just the average of the pi, right? So let's just call this i.i.d approximation Qn. So P is the mixture and Q is the i.i.d. And the main target of this work is just to show that this approximation makes sense. It's quantitatively accurate. So to measure the distance between P and Q, throughout this talk, I will be using several statistical distances. So let me just write it here. Since we have a whiteboard. So I will be considering, let's say, several different distances, including the TV distance. Let's write out the definition in case some of you forget. We can also consider the Corbett-Leibler KL divergence, and also the chi-squared divergence between P and Q, which is defined as Pi minus Qi squared over Qi. So by the way, by Pinker's inequality, we know that the TV squared is upper bounded by KL, and also by some convexity argument, we can argue that KL is upper bounded by chi squared. So the quantity gets larger. And in this talk, we will be providing upper bound for the largest one, the chi-squared divergence. But occasionally, we will also be working with TV or KL. And the ideal scenario, what we really want to show here is that maybe some chi-squared divergence between Pn and Qn are actually something independent of that. Which means that although both distributions are very high dimensional, their statistical distance is actually a constant. Meaning that actually they are, in probability terms, they are contiguous to each other. So what are the motivations of considering such a permutation mixtures? So in this talk, later we will cover, at least, the following applications. So first of all, there are statistical and information theoretical applications directly involving permutations. For example, in statistics, sometimes one just explicitly impose permutation priors. In information theory, actually recently there is a channel coding problem called the noisy permutation channel. And we'd like to understand what is the capacity of that channel. And there are also some other problems which are not directly related to permutations. And we will be talking about something called the empirical base in statistical framework, and also something like called the Finetti-style theorems in probability theory. Concerning exchangeable distributions. Although there are some other things we will not cover in this talk, the bigger picture of this talk is actually to provide some new techniques. So we'd like to, through the lens of the permutation mixtures, we'd like to provide some new techniques for understanding the general mean field approximation. If you feel like, okay, there is a weak dependence, but you like to quantify it. And also to understand what is the information geometry of high-dimensional mixtures. I mean, suppose I have two general high-dimensional mixtures, and I suspect, okay, maybe they are close. Then what is the right technical tool to establish that? Provided that actually many existing tools will fail. So to support my claim just now, let's look at a toy example. So in this toy example, let's just assume that, okay, half of the PI, the distributions are actually normal mu1, and the other half is normal negative mu1. Just, two component, Gaussian mixture. Okay, so in this case, both distributions, the Pn and Qn, will be a Gaussian mixture. A high-dimensional Gaussian mixture will be some distribution mu p or mu q convoluted with a n-dimensional Gaussian. And the only difference between mu p and mu q here is that mu p is actually the distribution of n uniformly random draws from some multiset without replacement, and mu q is the sampling with replacement. Okay, so those are the distribution mu p and mu q. Those are the mixing distributions. Before we convolve with the Gaussian mixture. So under this toy example, let me first tell you that the test result actually tied within multiplicative constants. But the chi-square divergence between Pn and Qn here, actually have two phases. So when mu is small, it turns out to be the fourth moment of mu. And when mu is large, it turns out to be something like e to the power mu squared. So the first key thing I'd like to emphasize here is that, in either of the regime, actually this chi-square divergence independent of dimension n. So even if the dimensionality is very large, even if infinity, it turns out the chi-square divergence is still a constant. A constant, depending on mu. The second thing here is that, so even if we are looking at those two high-dimensional mixtures, the result turns out to be smaller than the one-dimensional divergence. I mean, even if I compute the chi-square between two normal distributions in one dimension, for example, this actually gives us mu squared when mu is small. And on the contrary, actually we have mu to the fourth power. And later we will explain why it's a fourth power but not a square. And third, maybe more surprisingly, I mean, this is a very simple example, a toy example. But as we will show next, many existing approach will fail for this toy example. So we even need some new techniques for this toy example. Let me enumerate some of the ideas that we can try. So the first thing is actually something like, mixture distributions are too hard. I would like to do simple distributions. Let's do reduction to simple distributions in the sense that, we have, now let's work with KL for simplicity. So we have two mixture distributions in the argument of KL. And we know that KL divergence is jointly convex. So we can actually put out the expectation outside. And because the expectation only concerns the marginal distribution, actually we can put any coupling between those two distributions. And after we do the calculations, after we do the minimization of all coupling, we get something like the squared Wasserstein-2 distance between the mixing distribution, the mu p and mu q, which again, further we can compute is of the order something like root n times the mu squared. So the problem here is that, this result, first of all, grows with the dimension n. Second, the dependence on mu is also not right. For example, for mu small, we should have mu to the fourth power, not mu squared. So which means that, so if we like to reduce both mixtures to simple distributions, I mean, any such approaches, even if you can find out the best coupling will actually fail to get the right answer. Okay, then how about we do something a little bit more clever? So a little bit more clever thing here is that, then how about I only reduce one distribution to a simple distribution. So here I only reduce, the second one to a single normal, and I still keep some of the mixture structure for the first one. So here I can actually minimize over all possible families of distributions such that, okay, if I take the composition of this new Q and this design distribution, we just want the marginal distribution to be mu P. So I mean, it requires a lot of design. Okay, so for this two example, it turns out that this idea is pretty good in the sense that, so Yunzi Ding, was actually a PhD student of Zhang, and he in his thesis, actually he worked out this example. He found a pretty nice choice of those, the class of distributions, and says that, okay, turns out that for mu, this approach could lead to an upper bound mu squared. Okay, but this is still not new to the fourth power. Okay, this approach, could kill the dependence on n, but does not really lead to the right dependence on mu. And we can argue that, any such approach, no matter how smart we are in designing those distributions, this approach can only give us mu squared. Cannot give us mu to the fourth power. And what's even worse is that, okay, if we can go beyond this toy example, actually, this careful choice doesn't really generalize. We don't know how to do that in general. We know that how to do it in this toy example, but not in general. Okay, so that is basically, okay, the second approach. Okay, then the third approach is actually pretty smart and pretty recent. So if we cannot reduce either one to a simple distribution, then probably we need to directly solve the question of dealing with mixtures. Okay, we shouldn't think that, okay, there is a trick of playing around mixtures. So the canonical way to deal with the statistical distance between two mixture distributions is called the method of moments. In the past decade, that has found several applications in statistical work, for example, in L1 norm estimation in China law, in learning two common Gaussian mixtures in Maurice Hart and Eric Price, and also in some general Gaussian mixtures in Yihong Wu and Hongkong Yang, and also in some of my work in some entropy estimation work, example. So the idea here is actually to expand the Gaussian Lacoste ratio. Suppose C is a PDF of a normal distribution, a standard normal 0, 1 distribution. If we compute the Lacoste ratio between phi of x minus theta over phi of x and do a Taylor expansion around theta equal to 0, so the right-hand side will be the final Taylor expansion, and the coefficients for x, the derivative term here, hk of x here, turns out to be the so-called Hermite polynomials. Under the Gaussian family. And yes, Hermite polynomials enjoy several nice properties. The most significant one is actually the orthogonality under the Gaussian measure. So using this idea, okay, so this is a little bit long, but basically, most of them are actually equalities. So the only inequality step here is that, so if we do the TV distance, it will be actually the L1 norm of this power series here. So this expansion helps us to separate effect of, the variable x or z here and the theta, basically the mixing distribution. Okay, once we have this, we just apply some Cauchy-Schwarz. We have the expectation of some absolute value of something that's upper bounded by the expectation of something squared. And because of the orthogonality of the Hermite polynomial, we will arrive at something like this. So this factor just means that, okay, if the mixing distribution, two mixing distribution mu and nu has some close, first several moments, then actually the first several terms here will be 0. And the sum here will only take effect when k is larger than some given factor. So that is actually the key to show that, okay, sometimes the statistical distance is really, really small. Okay, so that is, okay, the illustration in one dimension. Okay, of course, the same diagram could be extended to general dimensions. So if we have a high-D n-dimensional Gaussian mixture, okay, everything precisely the same. The only difference here is that, okay, now we, instead of having the univariate moments, now we have some multi-indices. So the alpha vector factorial will be the product of each component factorials, and those m alpha mu will be the joint moment, of the random vector theta. Okay, so that is, so the application of maximum moment in high dimensions. However, again, application to our toy example. So first thing is that when alpha, when the sum of alpha I equal to 1, because nu p and nu q have the same marginal distributions, actually it means that the numerator will be 0. So the sum actually starts from the sum alpha I into 2. Okay, and that indeed suggests a mu to the fourth power dependence. Just means that the moments start to differ from from order 2. Okay, so this indeed suggests a mu to the fourth dependence. But the problem here is that in high dimensions there are so many cross-terms. I mean, if we even count the cross-terms of a given shape, like there are 2 1s and several 2s, let's say L-1 2s, then we get something like sum of alpha I equal to 2L, and we count the number of contributions multiplied by the moment difference, we will get something growing with them. Just for starting from L is actually 2. This somehow also explains why in the literature, maybe you only see maximum moment in one dimension, but you essentially never see maximum moment in high dimensions, because there are so many cross terms. We don't know how to deal with. Okay, last one is pretty recent. So the last one is called something like the method of cumulants. So this is a recent development by Shuyan and Stanford and X Wine, who is now at UC Davis. So they thought about the problem, by in a low degree framework, but their technique actually says that if we would like to upper bound some statistic distance between two Gaussian mixtures, actually we can replace the moment difference by the so-called joint cumulant. I don't want to delve into too much details about the cumulant. The only difference here is that, if you view the moments as some partial derivatives of some moment generating function, the cumulant is just, we add some log factor and change the moment generating function to a cumulant generating function. And, and the expression of a cumulant could be very complicated. And we can only, compute them through some recursive relationship. This sounds nice. And indeed, this idea has a better behavior for certain customs. For example, when the maximum moment idea fails, it turns out that, this one works pretty nice. But, there is a pretty subtle problem. The subtle problem here is that, if I take a look at the multi-index of this form, after some calculation, we can actually show that the dominating factor is actually something like L factorial. It's actually L factorial times something like the number of alternating permutations in combinatorics, which I don't want to talk too much. But the idea here is that, but we have cover squared, right? So cover squared over L factorial will give us a L factorial on the numerator. So it explodes really fast. So this is actually a diverging result. Again, we cannot use this approach even for the toy example. So this indeed calls for some new techniques to understand the high dimensional mixture distributions. So before we talk about the techniques, let's begin with some of our main results. So recall that in our general setup, we have n distributions, right? P1 to Pn, not necessarily two-component Gaussian mixture. So before we present results, let's define two quantities of this class of distribution P. So the first one is the so-called the chi-square channel capacity. So if we view P as a channel, from something from X to Y, then this channel has a capacity, chi-square capacity, something like this. So the only difference from the chi-square capacity with the Euro channel capacity is that I just replace the KL divergence by the chi-square divergence, or the mutual information by the chi-square mutual information. That's the only difference. And the second thing is that, I also define a larger quantity called the chi-square diameter. which is just an upper bound on the chi-square divergence between any pair of distributions. Okay, so those are just your two quantities. Yeah, and let's assume that, okay, those quantities are finite. Okay, that is actually one assumption, yeah, that we need to be made, meaning that, okay, the channel here is a little bit noisy, not too clean. Okay, and also one thing here is that, okay, those constants are dimension independent. We are talking about the 1D stuff. Yeah, has nothing to do with n. Okay, so the main result looks like this. So we have two upper bounds on the chi-square divergence in general between the permutation mixture and the i.i.d approximation. So the first upper bound, yeah, okay, so it looks like the sum of the chi-square channel capacity raised to the Lth power starting from L to 2. In other words, yeah, when this quantity, when the capacity is more than 1, then the dependence will actually be capacity squared. And you can ask what happens when this capacity is actually greater than 1. Then actually we should use the second bound. So even if the channel is rich enough such that, okay, the capacity is greater than 1, but still with a finite, or could be large, but still finite, chi-square diameter, then the chi-square divergence is still upper bounded by some quantity like this, which is still finite and independent of it.
Okay, I'm just on the first equation, channel capacity definition.
Yes. Mm-hmm.
So rho is so it's a mixture of these distributions P1 to Pn.
Yeah.
And
yes,
choosing one of those, but where is the x coming from? X is P. I don't know whether P.
Okay. It might be easier to think of P as theta. So we just think of the mutual information between theta and x. Well, I mean, theta could follow some any prior distribution rho, and x follows some distribution P indexed by theta. That might be easier.
Okay.
Yeah.
Do they need to assume P follows some prior rho?
I mean, super over that. The channel capacity is the supremum over prior distributions. I'm not assuming a prior distribution, but this is followed from the definition of channel capacity. Yeah. By the way, yeah, right. Actually, all of our results could replace the channel capacity by something like mutual information between some random, uniformly random index of 1 to n and the x. Okay, all our results could be replaced by that, but we think that, okay, it might be better just to upper bound it by the channel capacity. Yeah, because the P could be a larger family. I mean, easier to work with. Okay.
Such a question. This is like on the second figure measure, we like the two Gaussian example. Like my understanding, just a clarification.
Yeah.
I understand if you draw from here, then you are fixing half the data are drawn from one Gaussian and half drawn from another Gaussian.
Yes.
But if we directly draw from a mixture of Gaussian, there's no guarantee on the half of it.
Exactly. Yeah.
Okay. And so build on that, if we fix number of Gaussians, say like k Gaussians, and we let like P1 to Pn just choose from k Gaussian, and we let n converge to infinity. And intuition says that if like number of Gaussian components are fixed, as n converges to infinite, the distance should be like closer and closer.
So I think that the chi-square should go to 0.
Let's specialize if like we assume like P1 and P.
Okay, there is one caveat in thinking of that way, because the data is noisy. We cannot see we based on the observations, we cannot tell how many, I mean, positive parts we are choosing and how many negative parts we are choosing. So your intuition is suitable when you think about some clean case. So I mean, half of x is mu and half of x is negative mu. But here, half of the x is mu convolved with some noise, right? So somehow we have some estimation error if you would like to transform your noisy observation to your clean signal. That is actually precisely classified by the chi-square diameter. So when mu gets larger, the channel gets somehow that channel gets cleaner and cleaner, but this constant is still finite. It's large but finite. So somehow that is some caveat in thinking about that. So we are actually considering some noisy case for the permutation mixture. So this is the reason why we have distribution P. Yeah, so in the extreme scenario, P could be a delta measure, right? Yeah, so in that scenario, yeah, the chi-square diameter will be infinity. So yeah, our result, yeah, we are no longer apply. Yeah, because in that scenario, we can show that the chi-square must grow with it. Yeah, so that is a clean case. But we are focusing on the noisy case. So we have some noisy channel, essentially.
Some intuition highlights the curly P and the distribution of distributions when it's like finite.
Let me give you an example. Okay, so to apply this result, we only need, for a given channel, we just need to compute the two quantities, right? So for the two component Gaussian example, the two example, we can actually show that the chi-square capacity is upper bounded by 1 minus some very small things. So if we sum over this geometric series, we exactly get this. Okay, we have a little bit margin here, but that margin turns out to be sufficient and important. And if we can also think about some bounded Gaussian. Each pi could be a Gaussian measure. Well, okay, but the mean is upper bounded by mu. In this case, we can show that, okay, again, the Kaplan capacity, is, when for mu small is mu squared, for mu large it will be mu, and the diameter will be e to the power mu squared. So in this case, we can also show that, okay, upper bound, like, okay, mu small is mu to the fourth power, which is actually tight. When mu large, we will still get some finite number, but the exponent will be mu to the third power. We think that might be loose, but okay, currently we don't know how to improve over it. But still finite. Okay, let's go to some applications. That is the master theorem. We like to talk, we introduced here. So let's first look at some very direct applications. So in statistics, if we have a sequence model, something like xi independent following some distribution p at theta I, and suppose we like to estimate unknown parameter theta. So when proving Bayesian lower bound, one scenario is to assume that the underlying theta is random and it's just a random permutation of a known vector. Okay, that happens a lot in the somehow the norm constraint scenario. And the key quantity in the analysis for this scenario is actually to understand under this prior, what is the mutual information between theta, this permutation following permutation prior, and the observation vector. So applying our result, basically the idea here is that, okay, then you can pretend as if the coordinates theta, and even if it is permutation follow permutation mixture, you can just pretend as if the coordinates are independent. In the sense that, okay, under the permutation prior and under the i.i.d prior, actually the mutual information are pretty close. That's by a constant, even if n goes infinity. Okay, so that is something like when we have a permutation prior, and similarly in information theory, a Nurem marker in 2020 actually proposed the concept of so-called noisy permutation channel, to deal with some wireless networks and also some DNA sequencing stuff. So basically, he says that, okay, so let's consider channel. Well, the channel input is xn. This input comes through a DMC, give us Zn, and then we cannot observe Zn. And the output is actually corrupted by a random permutation noise. We get some random permutation of Zn to get Yn. So that is, the channel from xn to Yn, that is actually the noisy permutation channel. So the target is actually to understand what is the channel capacity of this channel. So in other words, we like to maximize over all possible prior distribution or input distribution of xn and compute with some mutual information. So for discrete channels, actually, he proved some attributability results by random coding. And also this, Jennifer Tang and Yuri Polinsky also showed the converse result, which actually won the 2022 SIT Student Paper Award. By showing that, this term, the channel capacity, looks like something like this. Actually, by the way, it grows with n on a logarithmic scale because the permutation loses a lot of information. Okay, so what is actually a generic way of thinking about that? I have to say that, although we have a nice converse bound, but the existing converse bound is actually proved by brute force. Actually, they are proving something like, okay, doing some very brute force anti-concentration inequalities and which cannot deal with any general channel P. So using our idea or using our result, it just says that, okay, I mean, we can just quantitatively, we can just pretend that Yn also have independent coordinates. Okay, and turns out that, okay, we can have a very general converse for permutation channels. It's upper bounded by actually something called the redundancy of some P tensor N, the i.i.d channel. Actually, technically, we need to have a converse whole. And if you are familiar with the term of the redundancy, actually, we know that redundancy is actually of the order log n, right? Yes, it's something degree of freedom over 2 times log n. And actually, this specialized for this discrete channel, it actually recovers the result. And the constant here is not important compared to log n. Okay, so that is a permutation channel. Let's also switch gears and talk about some final definite theorems. So definite theorem is actually a theorem in Bayesian statistics. So basically it states that, okay, so if we have an exchangeable process, exchangeable distribution, meaning that, okay, the distribution remains the same. If we permute, no matter how we permute the coordinates, any exchangeable distribution turns out to be i.i.d if we condition on a suitable latent parameter. Or in other words, this joint distribution could be written as a proper i.i.d mixture. Okay, basically if we condition on some latent variable theta, it becomes i.i.d. Okay, and people have already also studied, okay, the problem when, this is not an infinite sequence. It is also a finite sequence. So for finite sequence, this exact result does not exactly hold, and it can only hold approximately. Probably the most famous result is by Diaconis and Freedman in 1980, just showing the statistical distance between sampling with replacement and without replacement. And they show that, okay, if we have a sequence of less n, and if we look at the k-dimensional marginals, there exists a i.i.d mixture such that the KL divergence is upper bounded by something like k squared over n. So the cutoff point here is k is roughly speaking root n, and this is tight because of the birthday paradox. Okay. And there is also a really nice work by Sam. Actually, even earlier than Diaconis and Freedman, showing that actually this bound can be improved when the cardinality of x is small. So when cardinality of x is small, actually the dependence looks like k squared over n squared. Okay, so birthday paradox won't work out here for a small support. Actually this phenomenon has been refined recently in the information theoretical community by Johnson, Gavalakis, and Kotoyanis, for example, very recently. And okay, so how about our extensions? So first of all, I mean, we have 2 inequalities, right? And if we apply the first inequality, and just notice a very trivial one like chi-squared capacity is upper bounded by the cardinality of x, then we can actually also show essentially the same result as STEM, by showing that, okay, actually the chi-squared divergence between the exchangeable marginal and i.i.d distribution is, roughly speaking, k squared over n squared. Although I feel like, okay, this factor x squared might not be tight, it should be x, but we don't know how to do that. But the good thing is that, okay, actually we can extend to chi-squared using a very different argument, because previously all arguments are based on the chain rule, but chi-squared, we don't have chain rule for chi-squared. And more importantly, we can also develop some noisy definitive result. So if the original exchangeable distribution is actually the output, with an inverse of x and n, and also a product channel P, I mean P of Yn is still remains exchangeable. So suppose if the exchangeable sequence is corrupted by something, then automatically, for every k smaller than n, the chi-squared divergence between this exchangeable sequence and the i.i.d mixture scales like k squared over n squared. Just meaning that, okay, so a noisy channel essentially has some similar effect as a small support. So here I didn't say assume a small support. But we still have a k squared over n squared dependence. And for sure, we find it very hard to prove this using chain rule because the continual distribution will be crazy right now. k is anything smaller than n. We look at the k-dimensional marginal distribution of a n-dimensional joint distribution. Yeah. Okay, for infinite, of course. Okay. Okay. No log n, I think. What is log n? I don't know. Okay. Yeah. Okay. Yeah. Maybe I don't have time. Yeah. We can chat offline about this. But yeah. But if you know, okay, I need some time to explain what is redundancy is. But if you know, okay, that is turns out to actually grows like a log n. Yeah, it's a classical result in information theory in universal compression actually. Yeah, something is scales like a log n. Okay. Okay. Maybe okay. Last application. So yeah, the last application is called empirical Bayes. So empirical Bayes is actually a really interesting framework in statistics. Okay, so it has lots of empirical successes, but very limited in theoretical understanding. Okay, so the idea here is that, okay, we consider Bayesian setup. Yeah, but I mean, one criticism of a Bayes statistic is that, okay, the choice of prior, right? I mean, if prior represents my belief, then my belief might be different from your belief. Okay, so the idea of empirical Bayes is that, okay, how about we estimate the prior distribution from data in a generic way, which actually can be used, yeah, in many different scenarios, even let's say in choosing the hyperparameters in deep learning, for example. Okay, and this also provides a very interesting theoretical paradigm to understand some statistical work. Okay, again, let's consider a simple setting. Let's consider a simplest model where xi independently follows some distribution p theta I, and our target is to estimate theta. So the target here is that instead of finding a good estimate of theta hat with a small loss itself, we define a notion called regret. So the regret is actually, yeah, the difference between the risk achieved by theta hat and some oracle. So in reality, yeah, there are two very popular classes of oracles. So the oracle actually knows about the true parameter theta 1 to theta n. That is very powerful, but we restrict the oracle to take some statistical form. So in the simple oracle case, it just means it says that, okay, this oracle can only take, but must be a function of each individual data. And this function should be the same for different I. Yeah, although you know the entire data, but you are restricted to use the same function. Okay, and yeah, the second oracle called the permutation invariant oracle or the compound oracle. So someone said, okay, maybe your oracle is too easy. So let's consider that, okay, your estimator could be a general function of all your observations, all vector. But I require that your vector, I mean, in order to have a natural estimator, then this should be permutation invariant, right? I mean, if I permute your observation, then you should also, yeah, and also the estimate itself actually get the same thing. Okay, so in the literature recently, yeah, statisticians have studied a lot about against the simple oracle. So because simple oracle is simple, I only need to look at a 1D problem and try to propose the estimator. But that, okay, it gives a very small regret against the simple oracle. And it's a widely believed that, yeah, simple oracle does not really, it's not that different from permutation invariant oracle. Okay, yeah, because of maybe some weak dependence induced by mixtures. But I mean, how to formally show this? That the simple oracle is actually pretty close to permutation oracle. Okay, so the oracle analysis is actually pretty easy. So basically, I mean, as I said, yeah, both oracles are know the true parameter. Yeah, but because they are under limitations, actually we can equivalently think of that. The oracle only knows the multi-set, but not the order. Because they essentially cannot choose the order. And or equivalently, again, theta here follows a permutation prior. And in this case, it turns out that, okay, before we solve the question, we actually need to understand what happens, okay, a different upper bound for two permutation mixtures. So here, Pn minus I just means a permutation mixture, but I take out the ith component. So basically, we do a permutation mixture over the n-1 stuff. So using our proof technique, we can show that the TV distance between Pn minus 1 and Pn minus j, some Levin out analysis, turns out to be of the order 1 over root n. So if you apply a naive complexity analysis or triangle inequality, I mean, yeah, you can only get a constant. But because of this permutation, I mean, that hides the difference, the constant turns out to be 1 over root n. I mean, changes into 1 over root n. And this immediately implies that, so in empirical Bayes framework, suppose you have a separable loss. I mean, if your loss function could be written as, okay, yeah, your separate form, then for coordinate, the difference between the simple oracle and the permutation invariant oracle is actually of the order 1 over root n. And very importantly, this is little o of 1. So yeah, if you achieve some risk, some constant risk per coordinate according to your estimate, then I mean, your regret are the same. Yeah, no matter respect to this one or that one. So again, some permutation structure. Okay, I think I have 15 minutes left, and let's see how much proof I can talk about this, because I claim that we propose some interesting techniques. But at least let me go through the proof of the toy example. So as I said, okay, let's revisit the method moment approach, which is built on some Hermite expansion for the Gaussian ratio. Okay, so that is the thing. So the main idea in the proof is that, okay, so why should we use the density of normal 0, 1 on the denominator? So we have phi of x on the denominator. So why should we use that? I mean, you can say that, okay, we use that because that's simple, because that gives us a Hermite polynomial. But okay, is that because that we are using actually a wrong function here? Let's try out a different one. So how about I put the marginal distributions of P, yeah, let's call it the phi 0 of x, which is actually a 1D 2-component Gaussian mixture density. Yeah, what happens if I put this on the denominator? So in this case, because theta can only take 2 values, actually I can have such the following very simple expansion using hyperbolic basis using the tanh function. So again, we have some form like, okay, yeah, the second form, we have a product of something depending only on x and something only depending on mu, on theta, I'm sorry, right? So we have a hyperbolic basis. And previously we said, yeah, one advantage of Hermite polynomials is that they are orthogonal on the C. And we can also check that, yeah, use the new expansion, turns out that, okay, we only have 2 basis functions. These 2 bases are actually orthogonal on the C0. Okay, by some, direct check. And as a consequence of this, actually, it's very interesting to see that in our case, here, I mean, the one-dimensional distribution of theta actually is that uniform between, uniform on plus mu or negative mu. So the basis function involving theta actually has mean 0. While in Hermite polynomial basis, actually, this does not. Okay. So that is actually something really nice, because we are considering toy example, we have very nice expressions. So on the new basis, let's just try it out. So if we compute the Lagrange ratio between P and Qn, because Qn is precisely the i.i.d following phi 0, it's precisely something like that. And using this expansion, I will have something. The expectation of product, and if I expand the product into the sum of all subsets of n, we will have 2 separate things. Okay, just like the discrete Fourier transform, for example. Okay, we have this. And what is the benefit? The benefit here is that, so recall that we say that the tanh function and 1 are orthogonal on the phi 0. So which means that if we do the second moment calculation, these terms indexed by different set S are actually orthogonal. So we just have this self-squared and the expectation of the second moment of this tanh function, which give us the chi-squared capacity, raised to power, cardinality of S. So we also got some orthogonality, right? And the main benefit here is that now if we compute this quantity, the random vector follows a very simple distribution. Actually, we can explicitly compute it out. And we found that, okay, this expression, when the size of S, when L is an odd number, it's 0 by symmetry. If an even number is actually upper bounded by 1 over n to L, just by some algebra. So if we piece everything together, so in this sum, yeah, the number of s with size L is precisely n choose L. So we have n choose L times this cancel out. And okay, yeah, and in chi-square divergence, we take out the constant term. We are only left with this. So we solve the toy problem. But we can also immediately see the challenge moving forward, right? Okay, so what happens in general? Here, because theta can only take 2 values, so we have a very easy form. Yeah, that helps us to carry out all the calculation explicitly. What happens in general is that, again, we are doing the same thing. So we call this a doubly centered expansion. Or yeah, actually nothing fancy. So basically we are saying that, okay, we just take the likelihood ratio between Pi and the average P bar. We subtract 1 from that, we get some phi Ci of x in the remaining. And why do we call it doubly centered is that, so first of all, yeah, just by checking, yeah, you just take the variation with respect to P bar on both sides. You can see that this is centered in the x direction. So yeah, each phi of x for every I, yeah, has extension 0 when x follow P bar. And that's similar to the previous analysis. When we do the second moment calculation, we again has orthogonality and have something like this. Okay, so this is the first step. But okay, you may ask, okay, how should we deal with term in the in the expectation? So the second observation here is that it is also centered in the I direction, meaning that for every x, if we take the average over I, the index I is also equal to 0, again by definition. And we hope that, okay, this can also will lead to a small value. Okay, the intuitively why is that, I mean, yeah, if we don't have a product over S, right, then each term, each piece in the product actually has expression 0. So somehow we are taking the product, interpretation of a product of some mean 0 terms. And we hope that, okay, this will really lead to some cancellation that we'd like to see and make the cross terms not blowing up. Okay, so what are the details? Okay, so this is basically what we have. So the main key technical lemma here is that we need to make use of the permutation structure and prove something like this. So suppose we have a real matrix A, and we assume that all row sums of A are 0, and also all rows are normalized such that, okay, the sum of square is equal to n. Okay, this is just some normalizing property, but the key property is that all row sum being 0. Yeah, this is because of the W center property of C function. So I claim that, okay, I can expand this expression and it leads to something like this. So if we pick some random column, P, okay, from A and compute the following matrix permanent. The permanent is defined as this. So basically, it's closely related to the determinant. So this quantity will be upper bounded by some factor like the square root of n choose L. You don't need to remember this quantity. My main message here is that the centering is very important. So if without centering, you can just choose A to be all one vector. So each of the term here will actually give you L factorial. So the term on the left-hand side will be n choose L without square root. So basically, with centering, actually we save a factor of square root. And this square root, saving crucially prevents the final coefficient from growing with n. Actually, you will effectively reducing to the simple toy example. We have some cancellation like n choose L over n choose L. And of course, I'd like to show that this lemma is very hard to prove. So the proof is actually the main technical challenge. But the good thing here is that, okay, now we have a very specific math problem, no statistics or information theory anymore. Okay, so the proof of this consists of 2 steps. Maybe I don't want to, before time limitation, I don't want to talk the first one that too much. So this is actually a deep result by Stephen Banner, which was overlooked, could be overlooked by many people. So basically this means that, okay, to prove the inequality, it suffices to consider all A's with identical rows. The rows are exactly the same. So at the end of the day, we are reduced to some elementary symmetrical polynomial of some vector that sum into 0. So here is actually our key inequality. Actually, we have a Maclaurin-type inequality for this, for an upper bound on this elementary symmetric polynomials. So if xi sum equals 0, and assume satisfy some normalization constraints, then actually we can show that the magnitude of ELX squared is always upper bounded by some constant times n choose L. Again, think of x is if x is all one vector, then the left hand side would be n choose L squared. Again, a square root improvement. And also we can also prove something weak upper bound for a complex analysis, complex case, actually, which will be useful later. Okay, here we don't need to use that. We only need to use a real case. And this type of question actually has been studied recently, I mean, in the past decade by several theoretical computer scientists in understanding pseudo-random functions. And also the best upper bound we know is actually last year by Terry Tao. They can actually show something like this previously. By some nice differentiation trick. But this actually leads to an extra exponential factor like e to the L12. And crucially, in our application, we crucially need to drop this e factor to 1. That is actually the main technical difficulty. We encounter with this problem. So how to drop this factor from e to 1 for centered vector. And we do some analysis. So first of all, after some actually pretty non-trivial analysis, we can show that it suffices to consider a very small class of vectors. We can assume that x can only support on 2 points. So it will look like this for some k. So let's call it xk. And then we thought that maybe we are over. The rest is just a computation. We just work out the case, right? We don't have so many cases to work out. This function to be really challenging. So this function is related to many special functions in the literature. For example, some hypergeometric function. And we can also use many different techniques to try to upperbound it. For example, Stein's method, for example, Fourier analysis, but none of them succeeds. The key difficulty here is that there are too many cancellations happening here. So if we would like to do triangle inequality on every step, we will fail. We always have some plus and minus canceling each other. And we essentially need to do L-folds cancellation in our analysis. And also something very interesting. Then we do some experiments. So we fix some numbers n and L and understand what is the value of k. Let's compute value, the ratio between the target value and the target at the n choose L factor. You can see that up to some point, it will just be a constant. So the envelope here is a constant. So essentially that means that for many k, actually this quantity is large, which is very surprising because we previously saw there might be some, monotone relationship, right? Maybe we check some special point, then that's okay. But it turns out that this is the case essentially for every k, essentially. And now here comes the rescue. We need to actually apply the set point analysis. We need to lift everything to a complex domain. So an alternative representation of ELX is via Cauchy's formula. We can represent it as a contour integral or something. And the complex analysis, the set point method asks us to understand what are the set point of the term to be integrated. So that leads to the so-called set point equation. By solving this equation, we can work out what are the set points. So what happens in this scenario? So when k increases, so we have two set points. So one here, one here. And when k increases, these first meet and then stay on the complex circle, the unit circle in the complex domain. With a radius something like root L over n plus L. That is exactly explains why when k exceeds some threshold, actually, we get some, we see essentially the same scale. That's the set point. If that's the first time you see the set point method, I will use a metaphor from de Bruijn saying that, the contour integral is something like, you will have two villages on two valleys, and you would like to measure the altitude difference between two villages. And so you need to build a road that across this saddle. I know that. So I don't have time. Let's just complete the set point method and let's conclude. So the specific application here is that, Okay, I use a contour integral. Okay, just one sentence. Surprisingly, it's simple. Yeah, if we apply the AMGM inequality, we have a product, apply AMGM, we get it. Two-line proof for the complex case. Yeah, although, yeah, in order to shave off the root L factor, that requires some effort. We need to do a much more careful set point analysis. Yeah, but for the complex case with the root L factor, yeah, we are done. Okay, so that is complete proof for the first upper bound. Let me just say a few sentences about the second. The second idea, okay, is to express everything in terms of the permanent. And for permanent of matrix A, and for this matrix, we can say some properties, some such as the trace and spectral gap. And okay, the key technical idea to upper bound this stuff is actually to use complex normal random variables. We still need to resort to complex analysis by showing that, okay, certain quantity, if we introduce some complex normal random vectors, it's proportional to this. And by applying some AMGM, we get some really nice bounds. And then use the spectral gap condition to upper bound the further quantity. And also for individual SL, yeah, we also find something very interesting. I mean, we get, well, again, reduced to the elementary symmetric polynomial. Again, also with complex normal random variables. And that is where we need to use our inequality for the complex case. By using the inequality for the complex case, we can actually obtain some target upper bound, yeah, within some root L factor. And yeah, and that step will be used for empirical based analysis. So take home message, I mean, yeah, permutation will induce weak dependency quantitatively. Yeah, I mean, centered basis is the right basis to use in the method of moments in high dimensions. And if you would like to make your life less complex, perhaps you can live to complex domains. Okay, well, I also list some further questions, and yeah, but I don't have time to think about it, to talk about it. And thank you for your attention, and you can read our archive paper for details. Thank you. Yeah.
Questions outside.
Okay, yeah. Let's take questions offline. Yeah. Okay.
Thank you. That was very nice. I enjoyed it.
Yeah. Sorry to be a little bit over time.
No, that was good. That was very good. I'd like to read that sometime. But I had looked at some of this stuff, but not more from mean field analysis, like Schnitzman's propagation of chaos type.
I also look at, actually, they also show something like K squared or N squared stuff.
Okay.
Yeah.
There's something in there.
Intrinsically related.
Yeah, but that thing is very challenging.
Yeah.
You should get out because we have a class.